Hey everyone. In this video, I will be going through a between dyad moderator analysis within a structural equation modeling framework using the interaction approach. So in a previous video, I had shown how to test this same model, but using a multiple group structural equation model, where you were simultaneously estimating a model with and without children and among our heterosexual couples. But there is, again, another way to test that using an interaction approach. And so I will be going through that with you here today. So here is going to be our model syntax. And so if you've been with me, then a lot of this will probably look familiar. But if you're new to dyadic analysis and my videos, then I will briefly walk through all of the syntax. So first, you are going to load your packages. And so if you have them already installed, this is how you would load them. But if you haven't installed them, then you'd go down here to your console and then you type in install.packages, and then in quotes, put your in your package name. And so let's say we want to do Lavaan, and then you would hit enter. And that's going to download it. And then in your actual syntax file up here, you are going to load that. So you will see I'm using two packages here today. I am using Lavaan and I am going to be using Haven. And so Lavaan is structural equation modeling within R, and Haven is a package that allows you to bring over SPSS data files. And so speaking of Haven, I'm bringing over my SPSS data file here. It's called my data. And so this is my SPSS data file that I have specified in my working directory. So if you haven't used R before, and to set your working directory, which you will need to do each and every time you load R, you go to session, set working directory, and I choose directory, and this is my folder, right? So there's my data file right there, all right? Another way that I have found to set your working directory is actually you can go into your file explorer. And so if you just click on, this is where my data file is. If you just click on your previous syntax and you don't have R currently open, it will open that and automatically set it to your working directory. So that's a little shortcut that I just stumbled upon when using R. So here we are entering in our data. So we are telling Lavaan that we are going to be using this data file right here. All right. And so that's actually right here, the data file. And so we have 246 couples in our data file. So we're telling Lavaan that this is our data object. And so you will see that in future places in the syntax, particularly in our fit indices. So now we need to create our model object. And so I'm calling this between dyad moderation, and it's dichotomous. And so what we are doing here is we have our dependent variable, which is relationship quality. So how happy the male and female partners are in their relationship with each other. And then we are going to have depressive symptoms be our predictors. So we have relationship quality for males right here as our dependent variable, and relationship quality for females here. So you'll notice underscore M indicates the male report, and if it doesn't have anything at the end, that it is female report. And so these are the exact names as they show up in my data file. So these are not just random names that I've created. Rather, I am telling Lavaan these are the variables in my SPSS data file that I want to analyze. So we have the male reports of relationship quality being predicted by, so 1 tilde being predicted by depressive scores for male right here and for female right here. And we have our between dyad moderator. So a between dyad moderator is a variable that has the same value for both members of your dyad. So so your male and your female reports in our heterosexual couple example have the exact same values, but those values differ across different couples in your sample. So here I've created a dichotomous variable from the number of children that the couple has to whether or not they have children. together. So if they have children together, the male will say yes and the female will say yes, right? They're not going to disagree on that. And so that's for one couple one in our sample. For couple two, they might not have children. So essentially what we are looking at here is dyad to dyad differences and do the associations between depression and relationship quality for men and for women vary in intensity or directionality based on whether or not they have children, right? And so when testing moderation, we have our three pathways, our actor effect, which is right here. So male depression predicting male relationship quality. We have our partner effect, female depression predicting male relationship quality. And we have our between dyad variable, right? And this is where you only have it once, right? So because couples both have the same value, you only need to enter that variable into your model once. Actually, if you enter it into to your model twice, you're probably going to get a non-converged solution because those variables perfectly replicate one another. And so when you're trying to invert your matrices, it's going to say there's the exact same amount of information and you're going to run into lots and lots of errors. You're probably not going to converge. And if you do converge by some miracle, you'll probably get a non-positive definite matrix. All right, so those are our three main effects. And now we have two interaction effects. So we are going to multiply whether or not the couple had children by each person's report on depressive symptoms. So there's a variety of ways you can do that in Lavaan. I'm showing kind of the simplest way, and that's where you have your variable one, a colon, and then you have your second variable. So this regression coefficient is the multiplying the score for the number of whether or not the couple has children together times male depression, right? And you have the same thing down here, but it's female depression, all right? And you will also notice that in this example, we have the interaction for females also predicting male depression, right? So this would suggest that the effect of women's kind of partner effects on male depression might vary across whether or not women have children or not, or the couple has children, I should say. All right. So you do want to specify all of these pathways. Some people might say, I don't think that there's going to be a hypothesized pathway here. I don't know why, the interaction between female depression, whether or not the couple has children or not, is going to predict male relationship quality. But you do want to test these pathways initially. And if they're non-significant, then you can remove them from the model and do a likelihood ratio test or a chi-square difference test in order to empirically evaluate that hypothesis, right? And so we're going to have 5 total terms, our actor and our partner effect, the effect of our between dyad variable, and our 2 interaction terms, all right? And then we're going to have that for males, and we have literally the exact same syntax for females. The only difference is in the dependent variable, where all of this is predicting variation in female relationship quality. And then here I have the covariance between relationship quality among male and female partners to account for the non-independence, right? So the more males are satisfied in the relationship with their partner, probably the more likely it is that their female partners are also going to be satisfied, right? And so you'll notice I don't specifically specify the covariances between all our independent variables. Lavaan can get a little bit finicky with creating interaction terms in this way. And so if you want to actually estimate those covariances in terms of wanting to know what they actually are, you can create an interaction term kind of the old-fashioned way by creating a new variable in your data set or in the context of Lavaan and using that to specify your model. So I'm not doing that here since that's an extra step and not the focus of the video. So we can go ahead and we can run this. All right, so we will make this a little bigger. And so you should have a saturated model. And so in SEM, a saturated model is where you have 0 degrees of freedom. You are placing 0 restrictions. You are placing 0 constraints on your model. You're allowing all your means, your variances, and your covariances to be freely estimated, right? So each one gets to kind of have their own unique identity. They're all kind of snowflakes. No single one is the same, right? And so you will not have, as a result, an ability to evaluate the extent to which your model fits your data. So your CFI and your TLI will always be 1. Your SRMR and your RMSEA will always be 0. So I really only use this output here to double check my syntax. So if I see a degree of freedom here when there really shouldn't be one, I know I've made a syntax error. Otherwise, all of this information isn't all that helpful. I might consider the log likelihood, when I start comparing models and things like that, but overall, it's not that important. So moving down into our findings, we have our male outcomes right here and our female outcomes right here. And we can see that there's a significant actor effect, a non-significant partner effect, and we can see that there is not a main effect or significant effect of the between dyad variable number, whether or not the couple has children, or the interactions between depression and children for men, okay? And so you can potentially interpret this effect, but I tend not to, because I don't find it all that interpretable when there's interactions, because we are intentionally inducing multicollinearity. And so this parameter kind of changes its meaning because we have other sources of the same information elsewhere in our model, specifically in this interaction term. So I don't find interpreting main effects all that relevant or all that important when you are testing moderation in this way. So we'll scroll down to females, and you'll see that we have some, again, potentially uninterpretable main effects where we have an actor effect that's significant, or a partner effect that's significant, excuse me, and an actor effect here that is significant marginally, just barely, p equals 0.049. And you'll see that we have a successful or significant interaction. So if you were with us in the multiple group SEM video, we found this exact same finding. So our p-values were slightly different. So because we were testing these interactions in slightly different ways, but we end up at the exact same result, where there are differences in the effects of female depression on female relationship quality, depending on whether or not they have children, right? So we do have a significant interaction. And then down here, we can look at our R squared, all right? And so if we want to estimate the unique contribution of the interaction term, because oftentimes that's important for statistical power, because moderation is exceptionally difficult to do, then we would calculate the semi-partial correlation coefficient using these values, and that's how you would determine the specific amount of variance that this interaction term accounts for. All right, so that is the idea behind between dyad moderation. One thing that we could do, and we'll only do one step, is you can begin to constrain these pathways to be equal. So we can begin to see whether or not that significant interaction for females is significantly higher or lower than that non-significant interaction in males, since that provides kind of an empirical test of that. And so in this model, you'll see that I have actually coded up those both actor and partner effects, where I'm constraining the actor effects to be equal across dyads and the partner effects to be equal across dyads. And so I'm actually going to take off the partner effects here. So we can just test those actor effects, since that's where our kind of significant interaction was. Now we want to test whether or not they are significantly different from one another. And this is beginning to test a three-way interaction between gender, relationship, or gender, depression, and relationship. And then a number of whether or not the couple has children. My apologies. The previous example was using relationship length when I was testing a continuous between dyad moderator. All right, so we can go ahead and run this. So here we should have a degree of freedom, because we are constraining. So I'll go back to the syntax. We are constraining those actor effects to be the same value. All right. And so before I said, how every snowflake is unique and there are no two alike, everything is freely estimated. Well, that's not happening in this model. We are telling the interaction terms that you have to be the same. We are saying you are no longer snowflakes. You now have to be behaving the exact same way. You no longer have your own unique identity. The two of you can negotiate yourself what your identity is and who you are and how you want to behave. But for the most part, you have to be exactly the same. So that's where our chi-square difference test or likelihood ratio test comes in. And when you have a saturated model, this is the finding for your chi-square difference test. You could always, type in your lab test. So we'll scroll down here, and if you do lab test LRT, then you would just type in the fit between your two models, and you could compare them. But that is not necessary here because we had 0 degrees of freedom, and so this is the test in and of itself. Be very careful. Do not misinterpret that with the baseline model. What the baseline model is it's you can freely estimate your means and your variances, but all of your covariances are set to 0. And so obviously that should be a really bad fitting model, because you're kind of hypothesizing that there's no relationship among any of your variables. And so if you're putting variables in a model, unless you're just throwing, spaghetti against a wall and seeing what sticks, this is going to be significant, and you're going to be hard pressed to make a worse model. All right. So don't confuse it with the baseline model. Don't use the baseline model. Use the model test user model results. All right. And so I don't find CFI, TLI, RMSEA, or SRMR all that helpful in these models with small degrees of freedom, because either they're going to behave really, really well, like here, or sometimes your RMSEA is going to be like 0.10. All right. So Dave Kenny's done some research on looking at the model degrees of freedom and how does your RMSEA perform. And it does very poorly in models with small degrees of freedom. So I kind of ignore that. All right. And you can kind of see here, right, that we have our labels here. And now when we constrain that effect to be equal, actually both are significant now, right? So essentially here what you're doing is you're kind of taking a dyadic average. It's not the exact same thing, but that's kind of a way to kind of at least conceptually understand it. We're taking a dyadic average of those parameter estimates. All right, so if we actually scroll back up, we can take a gander at what the interaction term was. So we kind of have, negative 0.06 here, and we kind of here we have negative 0.28, and we'll scroll back down here, and we're kind of in the middle, right? So 0.28 minus what gives us negative 0.17, that's about 0.11. And if you subtracted 0.11, or I guess in here added 0.11, we get around negative 0.06, right? So it's not exactly a dyadic average, but it will be fairly close to it. And so what that does is that actually brings this effect to be significant. So we could interpret that as there's a significant interaction for males, but the more likely explanation here is actually that our model is underpowered to actually detect the differences between these males and females, right? So we don't have a great sample size. I think we have around 150 without children, around 96 with children. So we don't have a whole lot of statistical power to detect the differences. So we can interpret this as significant interactions for both. But again, I think the more likely outcome here is that we are actually underpowered. We do not have enough sample size to detect that small of a difference. All right, so we are potentially making a type 1 error here in our analysis. So even though the chi-square difference test was non-significant, and that might say, oh, hey, we can actually constrain these to be equal and it doesn't hurt the model, so we're good to go. I think the more likely explanation, just kind of eyeballing the coefficients, is that we're actually underpowered. All right. So again, take a look at this. The standardized and the unstandardized, they happen to be the same. There's a pretty big difference between negative 0.06 and negative 0.28. So I would actually be very uncomfortable, despite statistics telling me that this is significant, that we can do this. I'd be very uncomfortable reporting that in a manuscript. And what I would most likely do is say, we constrained the interaction to be equal. We found that when we did so, the both male and female interactions were significant. However, we do not believe that these are adequately powered, and so we believe that this could be a type 1 error, and we actually believe that the interaction may exist in the population for females, but not for males due to the vast difference in coefficient effect sizes. So I would say something to that effect, to be transparent with the reviewers and the readers that we tested this, but we also believe that it's potentially not a true effect, and it should be replicated in future research. All right. And so I'm not going to go any further into this, but you could also constrain all the effects, the actor and partner interaction effects, to be the same. So you can have A1 here. We're not going to walk through the models, but we can, let me find my syntax. All right, here we are. We could have all of the interactions be the exact same, right? So we could do something like this, or the actor and the partner effects are the same, or we could constrain the actor effects to be equal, and we can constrain the partner effects to be equal. So we can do that as well. So there's a lot of flexibility in testing these models, and unfortunately, researchers, they don't test for these between dyad moderators, and then they don't take these three possible three-way interactions they don't test them. And I think that's kind of holding us back in terms of a better understanding what is actually going on among dyads. So hopefully this video has been helpful in understanding between dyad moderation using an interaction approach.